So welcome back for the fourth module of this week. So in the last module we had started talking about the maximum entropy classifier. What is the basic principle for using this maximum entropy classifier? Okay, and we saw that we can use any heterogeneous set of features that were not allowed in the earlier model like HMM. So today I will start by taking a simple example that will give you some idea on how maximum entropy classifier actually works for a simple classification problem. And then we will see how it can be used for a sequence tagging problem. That is, I am given a sentence. So this is my problem for part of speech tagging. I am given the sentence. For each of the words, I have to find out what is the actual part of speech tag for that. So right now, what we had seen in maximum entropy classifier, it gives me a probability on the class y given a context. Okay, so for each individual word, for the context around that word, I can predict what is the appropriate part of speech category. But once I am given the sequence, how this model will be actually utilized. So there it has a special name called MEMM, maximum entropy Markov model, and we will see what is the algorithm for using the classifier that we have discussed for a sequence tagging problem. So now starting with a simple problem on how to use maximum entropy classifier. So this is a practice problem, so you can try it on your own, but I will try to give you certain hints. So the problem says, you want to use maximum entropy model for part of speech tagging, and you are trying to estimate probability tag given word. And in this hypothetical setting, you can assume that there are only three possible tags: determiner, noun, and verb, and the word can belong to any member of a set V, that is your vocabulary. And vocabulary contains the words a, man, sleeps, and some additional words. So in this problem, it does not matter how many words are there in your vocabulary. Now, the constraint given is as follows. So the distribution that you will find, probability tag given words, should give the following probabilities. Probability of determiner given the word a is 0.9, probability of noun given the word man is 0.9, tag v given sleeps is 0.9, d given any word other than a, man, and sleeps in the vocabulary is 0.6, and same for other two constraints that are given here. So remember, that's what we did in the case of maximum entropy classifier. You are given the data, and from the empirical distribution you extract certain facts, and now you want to find out a distribution that resembles that empirical distribution. Okay? So now I want to find out probability tag given word such that these constraints are followed. So now how do I go about building my maximum entropy classifier? This is the problem. So now it is said that all of the probabilities that are not given, suppose they take some value such that probability tag given word is 1 for all possible tags. This is the normalization constraint, that probability for all the possible tags for a given word should add up to 1. Okay. Now there are certain questions here. So the first question says is that, so you are given this problem settings. Now try to define what will be the features of your maximum entropy model given these constraints. Okay. And the problem says that mark your features as some f1 and f2, and each feature should have the same format as we explained in the last class. Okay. So that is, each feature is a function of x and y. X is the context around the word, and y is the particular class or tag. Then the next question says, for each feature fi, assume a weight of lambda I. Now write down the expression of the following probabilities. So what is the probability of d given cat in terms of your model parameters? So the parameters are mainly lambda 1 to lambda 6. Similarly, find out probability of n given laughs, probability of d given man. Finally, the problem says, what should be the values of the parameters in your model, lambda 1 to lambda 6, such that you obtain the distribution as shown in the question. Okay. So this is my problem. So let me try to solve it in steps. So this is the first problem. What should be the features of my model such that they resemble this distribution? So okay. So we have extracted certain facts from the data. So let me write down the first fact. Probability d given a is 0.9. Okay. So now I want to find out some feature fxy such that it can try to match this particular constraint. So X is on my data, so this is on my word and the context, and Y is the tag. Okay. So now what am I observing in this particular example? I am observing that when the word is A, then the tag that I give is D with a probability of 0.9. So what kind of feature will try to model this? So my feature should be fxy. So I can use a feature word, so that is my x is equal to A, and tag, that is my y, is equal to D. Okay. So that encodes both A and D that I am observing in this empirical data. Okay. And this you can call as your F1. Word is A and tag is D. So this is a binary feature. So whenever you will see word as A and tag at D, you will put it as 1. So to make it explicit, you can say F1 is equal to 1 if this happens, is equal to 0 if this does not happen. Okay, I am not writing it in this paper. So now I have to define some other features, right? And the hint is that 6 features will make my task easy. So that is like sufficient hint. You have 6 possible constraints and you have to define 6 features, one for each constraint. So let's take the second constraint. So second constraint is probability and given man is 0.9. Okay. So for this constraint, what will be my feature? Again, so F2 would be word is equal to man and tag is equal to n. Now same way you can do for your third case. So F3 will come out to be word is equal to V and word is equal to sleeps and tag is equal to V. Now what would you do for your fourth observation? What is that? Probability D given word is equal to 0.6 for word in vocabulary minus A, man and sleeps. Okay, for any word other than A, man and sleeps. So what would your feature? Again you will have a similar feature, F4, word is in. So let me call this as V prime, V minus A, man sleeps. Let me call it as V prime. Okay, this is my V prime. So word is in V prime and tag is equal to D. Okay. Similarly, my F5 will become word in V prime and tag is N. F6 word in V prime and tag is V. And these become my 6 features that will try to model the distribution. Now so this is how you will select the features given certain facts about the data. So see here, I am not doing anything for matching these numbers right now. So that I will try to do using my lambdas, that the feature weights that I have to choose. So the next part of the question says is that now give weights. So suppose this is lambda 1, it has a weight of lambda 1, lambda 2, lambda 3 and so on. So each feature Fi has a weight of lambda I. Now try to find out some probabilities in terms of the model parameters. So let me take out the first question itself, that is probability of D given cat. I want to write that in terms of model parameters. So what will be this? Probability D given cat. So now in terms of my maximum entropy model, how do I write this particular probability? It should be e to the power sigma lambda I fi divided by a normalization constant, and z should be such that this will add up to 1 for all the 3 tags. So probability d given cat plus probability n given cat plus probability v given cat should be 1. So let me take this particular y, okay, and let me focus only on this, and I will talk about z later. So now, so this is sigma lambda I fi xy, x here is cat and y is d. So now fxy, so each of the 6 features are binary features. So they will take either 1 or 0, and lambda 1s are just given to me, and their values are not given. So I can just take lambda 1, lambda 2 and so on. So now what will be this value? Okay. So let me take the first feature. So first feature is here word is A and tag is D. In this case my word is cat. Okay, so clearly this feature is not 1. So for f1 xy it will be 0. So lambda 1 times 0 plus lambda 2 times. What is my second feature? Second feature says that word is man and tag is n. Again this is 0. f3 word is sleeps, tag is v, again 0. f4. So my feature f4 is word is in v prime. Is this word in v prime? Cat is not either A, man and sleeps, so it is in v prime, and tag is D. So this is actually 1. So word is in v prime and tag is D. So lambda 4 times 1 is, I will not write f4 here, f4 is 1 in this case, plus lambda 5. Now you will see in feature 5 and feature 6 the tags are different, they are n and v, so they will again be 0 plus lambda 6 0. This comes out to be lambda 4. Okay. So now what is my probability? It will be e to the power lambda 4 divided by z. Now how do I find out z? Now to find out z, you have to actually compute the other 2 probabilities also. So you have to compute probability n given cat, probability v given cat, okay, and then you can make this plus this plus this is equal to 1. So let me quickly do that. So what will happen for when you compute probability n given cat? The first 3 features again use a word A, man and sleeps, that is not here. From 4th features they are using the words in v prime. So the word cat is in v prime. So the features can be one from f4, f5, f6, but now I have to see the tag. For f4 the tag was D, for f5 the tag was n, and for f6 the tag was v. Okay, this was n, this was v. So for n given cat, f5 will be 1, and v given cat, f6 will be 1. So can I write probability n given cat? This will be e to the power lambda 5 given z, and this will be e to the power lambda 6 divided by z. Okay. Now you can compute what is pt given cat, because this 3 will add up to 1. So put in the constraint e to the power lambda 4 plus e to the power lambda 5 plus e to the power lambda 6 divided by z is equal to 1. So that gives you z is equal to e to the power lambda 4 plus e to the power lambda 5 plus e to the power lambda 6. So this you can write as e to the power lambda 4 divided by lambda 4 plus e to the power lambda 5 plus e to the power lambda 6. That is your probability of d given cat in terms of your model parameters. Now in a very similar manner, I will suggest that you try out the other 2 cases. What is the probability of n given laughs and what is the probability of d given man. So again we have not used of the probabilities 0.9 and etc. that were given in the constraint of this question. So that I have to use in the last point. So what values do the parameters in your model take to give the distribution as described above? So that is what values they should take such that probability d given a is 0.9 and so on. Okay, and you may leave your final answer in terms of equations. So let me try to take only the first, try to satisfy only the first constraint. What should be the constraint on my lambda such that the first constraint of probability d given a is 0.9 satisfied. Okay, and the idea is very easy. You will, so just like we found out probability d given cat, you will now try to find out probability d given a. Okay, and that will be e to the power lambda 1. Yes, because first feature is 1 for this case, divide by z. Okay, now what is z? So for finding out z, I have to find out probability v given a and probability n given a. Now what is probability v given a? Okay, so again I will write 1 divided by z into something e to the power lambda 1 times f1 and so on. Now the word a is given only in the first feature. Yes, first feature says the word is a and tag is d. So the word is a is given. It is not given in feature 2, feature 3. Now what about the other features f4, f5, f6? They all talk about words in v prime where the word a is not there. So any of the feature cannot be 1 for this case. So all of them will be 0. So it will be simply e to the power 0. Okay, all the features are 0. Same happens with n given a. Okay, so they are 1 by z, 1 by z, and this tells me that probability d given a should be e to the power lambda 1 divided by e to the power lambda 1 plus 2, and that should be 0.9 to satisfy the constraint, and that will give me the value of lambda 1. Similarly, you will do for all the 6 cases and write down the constraints. Okay, so hope that gives you a good idea on how do we actually start building a maximum entropy classifier from some observations in the data, and how do we compute the probabilities. Now I'll take a very specific case. So that is why the paper written in 1996 by Ratna Parkhi on using maximum entropy model for power to speech tagging. So what I will show is that what kind of features they are used for power to speech tagging. Okay, so now this model is there. Now what is important to understand is that given a problem, what sort of features I should use to get a good performance. Okay, the model will work well if your features, the features that you have chosen make sense for this particular problem. So for power to speech tagging problem, what are the kind of features that he had used? Now given a new problem, again you have to go back and find out what should be the interesting features. You know now the format of features, how you should define your features. But what are important features will always depend on the particular problem that you are solving. So as we had said, so in the maximum entropy model, you choose a context around the word, from where you can choose your features. So in this case, what is the context they have chosen? They have chosen the current word, the next 2 words, the previous 2 words, and the tags given to the previous 2 words. Okay, and that is interesting. How do you use this kind of features at the time of decoding? When given a sequence, you are trying to find out the tags, because you do not know what is the best tag for the previous word. Okay, so we will look at this this problem when we talk about the search algorithm, the beam search algorithm. That how do we make use of previous tag and previous to previous tag that are to be assigned, that are not yet assigned fully. Okay, but he has used all these features in all this context for defining its features. Now what are the form of features? So yes, just to give you another example, features will depend on the history or the context and the current tag. So it is 1 if the current word has a suffix of ing and the tag is vvg. That is one kind of feature, the suffix of the current word and the tag. So what are the other features? Okay. So now, so what is one interesting thing here? So he's divided it features into 3 parts. Some features are only for those words that are not rare, that are very common. Second sort of features are those words that are rare. Why does he define separate features for the words that are rare? Because these words may not be seen again in my text data, but I might see some other rare words. So can I use some of the properties of these words instead of using the word directly? Okay. So for the words that are not rare, they occur many times, he uses the word directly, wi is equal to x, and its current tag. This is the form of feature. But if the word is rare, he does not use the word directly, he says x is a prefix of wi, length of x is less than or equal to 4. So he uses all the prefixes of the word starting from 1, 2, 3 and 4. Same for suffix. Now how will that be helpful using the suffix? So for example, I have a word that ends in ed, but overall the word is rare. So can I use the fact that the word ends in ed? Okay. So that's why we are using the suffix here. Similarly for prefix. Okay. I can have something like in for making the opposites for adjectives and so on. Okay. So this can be captured by using this kind of features. Whether the word contains a number or an uppercase character or an hyphen. Okay. This is for rare words. Now he uses some other features for all the words. So what are the features? The previous tag is x and the current tag is t. So very generic feature, right? The previous two tags are x and y, current tag is t. Previous word is x and current tag is t. Previous word is x, current tag is t. Then similarly for the next word and next words. Okay. So now let us see what will be the form these features will take. So this is the generic form of the features. Now let us take a simple context and see what are the forms these features are going to take. So this is one context. Okay, I have a sentence, the stories about well-heeled communities and developers, and the tags are dt, nn and all, the part of speech tags are given to me. So this is from my label data. Now what are the values these features will take? So firstly I will differentiate between the rare words and not so rare words. Okay. So what can be the rare words here? For example, the word well-heeled here is a rare word. Okay. And other words like stories, communities, developers are not rare. So for the words that are not rare, what feature am I using? The current word and the tag. So my feature could be the word is stories and tag is nns. So on. For the word well-heeled, I will use the suffix and prefix. So w is a prefix of the word and tag is jj. W is a prefix, tag is jj. Similarly, ed is a suffix and tag is jj and so on. Okay. And then there will be some features for all the words, like for about and well-heeled. What will be the feature? The previous tag is in and the current tag is jj. The previous two tags are ns and in and the current tag is jj. The previous words or the word is stories and well-heeled, about and well-heeled and so on. So you can use all these features. So here are all these features, right? So this is prefix and suffix for the rare word well-heeled. And there were other things like wi contains hyphen, that is in the case of well-heeled, and tag is jj. Okay. So now that's how you will write down all your features from your data, and you will learn your parameters, lambdas and all, and at runtime you will use again these features and the parameters to find out the probability of the tags. Okay. So hope this gives you some idea on how can you choose your features for a given task. Now let me go to the search algorithm for this Maxent model. So this we had discussed earlier also, but we did not discuss in full details. So I am given a sentence w1 to wn, these are the words, and I want to find out the probability of tag sequence t1 to tn. Okay, and we said that we can write it in this form, multiplication of probability ti given xi is the context for each individual word. Now the problem here is, and you can use some tag dictionary that says for each individual word what are the possible tags, similar to what we did in the case of Viterbi decoding for HMM. Now, what is one particular problem in this case? So as such, it looks as if you can do it independently for each word, right? For the first word, I can find out what is the best tag, multiply it with the best tag for the second word, and so on. Now, what is one problem with this approach? So let me just give you one simple example. Okay. So this is a hypothetical example. So let us say that we have word 1, word 2, word 3. Okay. And word 2 can take two tags, IN and JJ. And word 3 can take, to keep it simple, it can take a tag like VBZ and maybe something else like VBG. Okay, they may not be possible, but just a hypothetical case. Now suppose by using this algorithm or doing it independently, you found out that for W2, IN gives some probability and JJ gives some probability. Now in W3, what would happen? Some of the features might depend on the previous assigned tag. So for VVZ, you might want to use what is the tag assigned in the previous word. Okay, so that means choosing the probabilities, the best probabilities at this point may not be the best. So choosing the tag at this point may not be the best, because at the next step you are using the tags and the probabilities can change. This can happen that IN is giving the better probability at this point, but when combined with VBZ, JJ gives a better probability. This can happen. Okay, so that means I can find out the probabilities, but I have to use the probabilities and the tags in the next step also. Okay, so this is not fully independent. I cannot just choose IN and forget about it. I have to remember what is the probability. Next time I will choose IN VBZ, JJ VBZ, and try to compute the probability for VBZ, multiply it with the previous probabilities. And how exactly we do that, I'll show you using the beam search algorithm. So what is the beam search algorithm? So your test sentence is containing words like W1 to Wn. Okay, and let us say that for the ith word, Sij denotes the jth highest probability tag. Okay, this is a tag sequence up to the word Wi. Now how does the algorithm work? So you have the words W1 to Wn. For word W1, you have S11, S12 up to S1n, top and highest probability tags. Okay, so we will compute the probabilities, and this is easy. Again, you will use the features here, which feature is 1, which feature is 0, then you will do the normalization. You will compute all these probabilities for each of these tags. Now the important thing is, how do you go to W2? Okay, so one thing to understand is that you can probably not keep all the possible tag sequences, because assume that each word can take on an average k tags. So if you have n words, the tags would be of the order of k to the power n. Yes, k to the power n. So this will be exponential in the length of the sentence. So you cannot keep all the tag sequences. So you might have to make the choice of the best sequences available at this point. That's what we do in beam search. So at each point, I will select what is the top, say top capital N sequences at this point, and how do we select that? So that is the next part of the algorithm. So initialize I is equal to 2. Okay. So now you are at the second word. Generate tags for Wi given as I minus 1j as the previous tag context, and append each tag to as I minus j to make a new sequence, and then continue for all the tags. Now what does that mean? Initialize I is equal to 2. So that is your second word. Now generate tags for Wi, yes, given as I minus j as the previous tag context. What is I minus j? I minus 1 is S1 and j. So let me take this as the previous context, and suppose this has again some tags like I'll just write some tags T1, T2, T3. So S11 and T1 becomes the first sequence. S11 and T2 becomes the second sequence, and S11 T3 becomes the third sequence. Similarly, S12 T1 becomes fourth sequence, and so on. Okay, so in this case there will be 3 times n sequences. So this you can take in general case. This may not be one tag, this will be a sequence up to this point. So these are all the possible sequences at this point. Now, for each of the sequence, you know what are the previous tags that have been assigned. Yes, so I know what are the tags assigned at this point. So I can use all the features. So if a feature says Ti is equal to something and Ti minus 1 is equal to something else. So I can check if Ti matches this and the previous tag matches this. Then only it will be 1, otherwise 0. So because I am choosing the context, I can compute all these features. I can compute these features, I can compute the probability for all the sequences. And now what I will do, I will select at this point what are the Si1 to Sin, what are the top n sequences at this point. Okay? And again I will go to the third word, again its tags, combine with all the sequences and choose top n from here. So what will happen, your space will not grow exponentially. You will always have top n sequences at any given point. So finally when you go to the final word, you will get the top n probabilities or all the probabilities and you will select the best sequence. And now because this sequence contains the tag from the starting, you will find out the part of speech tag just from the choosing the best sequence at the last word. And that is your algorithm. So find n highest probability sequences by the above loop, set this accordingly and repeat if I less than equal to n and return the highest probability sequence Sn1 for the last word. And this is your maximum entropy. This you can call as your maximum entropy Markov model. Okay, instead of maximum entropy model is general classifier that can do for each word individually. But when you are trying to apply it for a sequence labeling problem for a sequence, you use this maximum entropy Markov model. Okay, so this was maximum entropy Markov model for you. Now in the next lecture, I will take one simple example of this search, and I will quickly cover the model of conditional random fields, that is one of the state of the arts in sequence labeling task. And what we will show, there is some problem with the maximum entropy model that conditional random fields try to handle. Okay, so thank you. I will see you in the next class.